Hello there. In this video we're going to continue our discussion and conclude our discussion on our investigation of how to sort of analyze a polynomial in terms of its zeros by discussing a more in-depth discussion of the Descartes rule of sign. So remember from the last video we talked about what a sign change was. So I'm going to define a set S for polynomial P to be the set of all sign changes. So the set of all sign changes is going to be the set of all numbers, say L, such that the sign of AL is not equal to the sign of coefficient AL minus 1. And this is true for all L from 0, from 1 up to n. And we're going to define K to be the number of sign changes for this polynomial. So as we discussed in the last video, based on this number k, we can determine the possible number of positive real zeros for which this polynomial has, and we're going to extend that to the negative side in this video. Alright, so let's just do a quick review example of how to determine the number of sign changes. So let us assume we have a function f of x is equal to x squared minus 5x minus 7. So the sign of the leading coefficients, assuming that none of them are 0, are going to be, so it changes from positive to negative, so that's 1, changes to negative, that does not count. So in this case, there are only one sign change. So in this case, k is equal to 1. So what did Descartes' rule of signs tell us before? So if the number of sign changes for a polynomial p with non-zero coefficients is equal to k, then p has either k, k minus 2, k minus 4, all the way down to either 0 or 1, depending on if k is even or odd. Positive real zeros. Alright, so let's do an example of this analysis. So example 1, let us assume we have f of x is equal to x to the 5th minus 2x to the 4th plus 5x cubed plus 2x squared minus 7x minus 5. So let's look at how many sign changes we have here. So we have positive to negative, negative to positive, positive to positive, positive to negative, negative to negative. So we have 1, 2, 3 different sign changes. So k is going to be equal to 3. So this is going to be the sign of our sign changes. So that means f has either 3 or 1 positive real 0. So two possible sketches for what this graph looks like. So it's a degree 5, so we have 1, 2, 3, 4, 5, or something like that. Wait, no. So it's going to be 1, 2, let's see, got past 3 times. 1, 2, 3. There we go. So there's 1, 2, 3. So it bounces off on that last point there. 1 positive 0, so that's going to be 1, 2, something like that. So there's a 1. Right? And there's a couple other variations that you could have for this scenario. So let's talk about a second theorem, which is just a direct extension of Descartes' rule of signs. So theorem 2. So I'm going to define a polynomial q of x to be equal to the mirror image about the y-axis of this. And we're going to let the size of the sign change set of q to be equal to k. So we can apply the Descartes rule of signs on this polynomial q. But what does that say about the polynomial p? So since P is going to be the mirror image of Q, then the positive real zeros of Q are going to be the negative real zeros of P, right? So then P has K, K minus 2, K minus 4, or whatever number it ends greater than 0, positive or negative real zeros. So let's look into that in detail. So let us assume we have f of x is equal to, again, x to the fifth minus 2x to the fourth plus 5x cubed plus 2x squared minus 7x minus 5. So same exact example as last time. So I'm going to input x with negative x. So all my odds are going to change sign and all my evens are going to stay fixed. So this is going to give me negative x to the fifth minus 2x to the fourth minus 5x cubed plus 2x squared plus 7x minus 5. So let's count the sign changes for this polynomial. So negative to negative, negative to negative, negative to positive, positive to positive, positive to negative. So in this case I have two sign changes for the mirror image of f, right? So if this is the case, then that means f has either, and I'm talking about the original function f, not the mirror image. So f has either 2 or 0 negative real zeros. So again, it's a degree 5, so it either has 2 or 0. So it has either, so 1, 2, so it has something like that, or it has 0, so something like that. Right, so that's our 2, 1, 2, or 0 case. Right? So that's interesting. Now we can combine this logic to what we said about the positive real zeros. So remember, f has either 3 or 1 positive real zeros, right? So in this picture, this is our 1. This curve could come down and bounce off. So it could have 1. So these are the two cases for the 1 case. Now, what about the other case? So if it has 3 positive real zeros, so what would that look like? So if that's the case, that means we have 1, 2, 1, 2, 3, or 1, 2, 3, right? So is this possible? The correct answer is no, this is not possible because according to Descartes' rule of signs, you can either have 2 or 0 negative real roots. You cannot have only 1. So therefore, this graph is not a possible case for this polynomial function. So one can do some investigation on their own to verify that the true graph of this is actually going to look something like this. Right? So it has 0 negative real roots, and it has 1 positive real roots. So this is the true thing. So it could be possibly 3 or 1, but one can find that it's actually only 1, and it has 0 negative real roots, which is interesting. All right, so let's look at an example of how we can possibly use this and also a couple of the other theorems to factor a polynomial completely. So let's assume I have f of x is equal to, let's do x to the fifth minus x to the fourth minus x cubed plus x squared minus 6x plus 6. Let's count our sign changes. So there's 1, that doesn't count. 2, 3, 4. So positive real zeros are either 4 or 2 or 0. Let's look at our negatives. So f of negative x is going to be equal to minus x to the fifth, minus x to the fourth, plus x cubed, plus x squared, plus 6x, plus 6. Let's count the sign changes for that. So that doesn't count. This counts, that's 1. That doesn't count, that doesn't count, that's going to count. So the negative real zeros, 1. So this is useful. That means there's exactly one real negative 0. So if you can find what that one negative real 0 is, you do not need to possibly try any other negative real numbers into that polynomial. So that's extremely useful. So let us also recall the rational zeros theorem. So remember, the leading coefficient here is 1, and the last coefficient here is 6. So the factors of 6, as we know, are going to be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So let's see if we can find all the factors of this polynomial using this expression, and also combine with the strategies above. So let's start with 1. Let's do synthetic division since it's a little bit more quicker, or more quick. So 1, negative 1, negative 1, 1, minus 6, 6. So we're going to bring down 1. So 1 times 1 is 1, adds to 0. 0 minus 1, 0. That's going to be 0 minus 6. There's a remainder. So we started with a degree 5, so this is going to be a degree 4, right? So that means our polynomial, f of x, factors into, so if 1 is a 0, x minus 1 is a factor, and we have x to the fourth plus 0x cubed minus 1x squared plus 0x minus 6, or in more simplified terms, x minus 1, x to the fourth minus x squared minus 6. Okay. So we have one positive real 0, so x is equal to 1. So Descartes' rule of sign told us there are 4 or 2 or 0. So we've already ruled out that it cannot be 0 because we've already found 1, right? So there's either one more positive real 0 or there's going to be 3 more, right? So let's see if we can find those other ones somehow. So notice this is a special type of quartic equation because it's almost like a quadratic, right? So what we can do cleverly is we can let u be equal to x squared. So this actually equal to something like u squared minus u minus 6, which we should know actually does factor, right, in terms of u. So this is going to be equal to x minus 1, so that's going to be u minus 3 times u plus 2, right? Then we can switch back into x since u is just a dummy variable. So we have x minus 1, x squared minus 3, and x squared plus 2, right? We can use our difference of squares and sum of squares relationships for this. So we have f of x is equal to x minus 1, x minus root 3, x plus root 3, and then x plus root 2i, and then x minus root 2i. So there's all our 5 zeros, right? So there's our 2 positive real zeros here. There's our 1 negative real 0 here. Remember, Descartes says there's exactly 1 and negative root 3 is it. So by the fundamental theorem of algebra, if we only have 2 positive reals and 1 negative real, and our degree is equal to 5, that means the other 2, and remember they always come in pairs if the coefficients are real, and then we have our 2 complex conjugate zeros plus or minus root 2i. So that's just a summary of how to factor polynomial equations using the combinations of the fundamental theorem of algebra, Descartes' rule of signs, and the complex zeros theorem. Hope you enjoyed.